You know that smartphone in your pocket? Or the computer you're watching this on? Well, they're powered by literally billions of tiny, microscopic switches. We call them transistors. And the way they work on that tiny scale, it can feel like pure magic. But you know what? It's not magic at all. It's just some really, really cool physics. So let's peel back the layers and see what makes this incredible little invention tick. To really get our heads around this, let's start with this simple question. Think about a fire hydrant. How do you control that massive, powerful blast of water? You don't have to wrestle it or plug it with your bare hands, right? All it takes is a small, easy twist of a valve. The transistor solves this exact same problem, but it does it for electricity. And that's really the heart of it. A transistor is, for all intents and purposes, an electronic valve. The one we're going to be looking at today is called a bipolar junction transistor, or just BJT for short. And just like that water valve, it can do two amazing things. It can act as an amplifier, or a tiny signal can finally control a much bigger one, or it can be a simple switch, turning the flow completely on or completely off. So first up, we'll dig into this idea of the electronic valve. We're going to see exactly how this tiny little device gives us such enormous control over the flow of electricity. Okay, but you can't build a valve this small out of plumbing parts. Nope. You need special materials with some pretty wild properties. So, what are these magic ingredients? Well, the secret sauce starts with a process called doping. What we do is take a super pure semiconductor, something like silicon, and we intentionally sprinkle in just a few atoms of a different element. It's like adding a pinch of salt to a recipe. This tiny change has a massive effect on how it conducts electricity, and it creates two very special materials. The first kind is what we call N-type material. For this, the atoms we add have extra electrons that they're just happy to donate. This creates a whole bunch of free-moving negative charges ready to go. So just remember, N is for negative. And the other type? That's P-type material. In this case, the atoms we add are actually missing an electron, so they accept one from a neighbor. This leaves behind a little vacancy, which we call a hole. And this hole can move through the material kind of like a bubble in water, acting just like a real positive charge. So, you guessed it, P is for positive. And this brings us right to the name. A bipolar junction transistor is called bipolar for a very simple reason. Its whole operation depends on the movement of both of these things, the negative electrons and the positive holes. It's a team effort. Okay, so we've got our ingredients, N-type and P-type silicon. Now, how in the world do we put them together to build our valve? Well, it turns out it's all about making the right kind of semiconductor sandwich. The most common recipe is for an NPN transistor. First, we start with a heavily doped N-type layer called the emitter. Then we slap on a very thin, very lightly doped P-type layer in the middle. This is the base. And finally, we top it off with another lightly doped N-type layer, the collector. Each of these layers has a very specific job. The emitter's whole purpose is to emit or inject a huge flood of electrons. The base, that middle layer, acts as our control gate. It's the handle on our valve. And the collector's job is, well, to collect all the electrons that make it through. Now, if you take away only one single thing from all this, please make it this. The absolute key, the secret to the whole operation, is all about the design of that middle layer, the base. That's right, it has to be almost impossibly, microscopically thin. And I'm telling you, this isn't just a minor detail, it is the linchpin. It's the one thing that allows all the magic to happen. And here's why. So, the stage is set. We've got our NPN sandwich with its super thin base. Now, let's follow the electrons and see how this amazing structure pulls off the trick of amplification. First, we apply a couple of small voltages to get the transistor ready. You can think of this like priming the pump. It gets everything in position. Then, the emitter fires a huge stream of electrons into the base. And here's the clever part. Because that base is so incredibly thin, most of those electrons don't have time to do anything else. They just shoot straight across it, where a strong electric field from the collector is waiting to sweep them all up, creating a big, powerful current. And this picture just makes it perfectly clear. You see that tiny little control current we put into the base? Well, it only uses about 1% of the electrons. The other 99%, the overwhelming majority, zip right through that thin base and get collected on the other side. A tiny 1% input is controlling a massive 99% output. That, my friends, is amplification. We actually have a name for this amplification power. It's called current gain, or you'll often hear it called beta.
It's just the ratio of that big current you get out at the collector divided by the tiny current you put in at the base. And for a normal, everyday transistor, this number can be 100, 200, even 300. That's like 100-fold amplification. So yeah, it all comes back to this number, 99% efficiency. The fact that almost every single electron makes it across the finish line is what gives the transistor its incredible power. And it's all thanks to that one critical design feature, making the base layer impossibly thin. Now that we get the genius behind the design, let's zoom out for a second and just appreciate the massive impact of this device. This wasn't just some small step forward, this was a full-blown revolution. The whole story starts at Bell Labs back in 1947 with the very first kind of clunky point-contact transistor. Just a month later, William Shockley came up with the much more practical junction transistor we've been talking about, and this breakthrough was so profound, so world-changing, that the team won the Nobel Prize in Physics less than 10 years later. See, before the transistor, electronics ran on vacuum tubes, and these things were huge, they got super hot, they wasted tons of power, and they broke all the time. The transistor changed everything. It was tiny, it was efficient, and it was reliable. This one invention is what allowed us to create the integrated circuit, where we could pack not just one, but billions of these things onto a single chip. So the next time you pick up your phone or sit down at your computer, remember this. That tiny electronic valve, that little NPN sandwich, is basically the atom of the digital age. It's the fundamental building block that makes every single piece of modern tech possible. Our world would be completely unrecognizable without it. We've gone from one clunky device in a lab in 1947 to cramming billions of them onto a chip the size of your fingernail. The progress has been absolutely mind-boggling, all driven by our ability to make that critical base layer smaller and smaller and smaller. And that leaves us with a really fascinating question. What happens when we can't shrink it anymore? What will the next electronic valve even look like?